Here we go with Saxon Advanced Math Lesson 62.A, and this is talking about abstract coefficients. Let's do a quick review on what a coefficient is. A coefficient is the number that modifies a variable, right? So this is my coefficient. And in mathematics, in algebra, when we first started throwing in variables and constants and definitions like that, and you started using some letters of the alphabet. When we did so, we started out with X. That was our first one, right? That was where we started it all. Find X, over and over. Well, X is a variable at the end of the alphabet, right? X and Y, and we already understood that. When we started putting formulas together, when we wanted to put in a letter for a constant number, we automatically started using letters at the beginning of the alphabet. A and B and C for constants, X and Y for variables. And we kind of slipped that in on you, right? Like we never really talked about it. But what they were doing, and kind of by convention, or by, which is just saying it's not something that would naturally be found, but a bunch of guys and girls got together and said, hey, what would be a more universal way of doing this? Kind of like capital and lowercase letters. And they decided a long time ago, let's traditionally use letters from the front of the alphabet for the constants, and we're going to use letters from the back of the alphabet for variables, and that's where you end up with this. Okay, now, what this lesson has to do with is, if it stopped right there, right, that'd be the easiest lesson we've ever done. But what we're going to be doing is solving for abstract problems. So here we have an example 62.1, and we're solving for the variable y. Now, when we're solving for y, what we are doing so, we're finding what y is. That's what solve for means. But I don't have numbers in here, I have all letters, which means that my answer is going to have all letters in it. There's not going to be, oh, y is 6 for this problem. No, this y is going to be the variables. We're just going to define it in terms of y. So I look at this and I say, solve for y, and I have ax plus by equals c, and dx plus ey equals f. Now, for those of you who've been around with these videos for a little bit, you remember these are two systems of linear equations, and we solve systems of linear equations one of three ways. We can solve it with graphing, which would be really hard to do with this one. We solve it with substitution. Not too bad, but a lot of extra work. And we solve it with elimination. We're going to use elimination on this because it will always work out the same way, and it's easy to use. So let's go ahead and set that up. What we're going to do with elimination is we need the variables to cancel. Since we're trying to get y by itself, we're going to cancel out the x's, right? So what I'm going to do is I'm going to multiply the first equation by d and multiply the second equation by negative a. When I do so, I end up with dax, or adx, right, in alphabetical order. D times by is bdy, and d times c is cd. Now, this right here looks terribly confusing to a lot of people, but don't let it get you. If these were real numbers, somehow it would be easier. Don't let that bog you down. I multiply this next one by negative a. That negative adx, a negative aey, right, and a negative af. At this point, now I have something I can cancel. So I go ahead and add these two up. Adx and a negative adx is 0. bdy and aey, well, when we're doing this with normal elimination and numbers, this would be a, right? B and D, these are from the beginning of the alphabet. A and E from the beginning of the alphabet, they would be constants. And you would say, well, I know what to do with a constant. I'm going to add the constant numbers. But I can't, because these are variables at this point because of the fact they're letters. So I end up just writing them that way. bdy minus aey, right? And cd minus af. So at this point, it doesn't look like we've helped ourselves at all, except that we've gotten all the y's on one side, all the non-y's on the other, and we have a y and a y that I can now factor out. So I factor that y out to the front. That leaves me with a, bdy divided by y is bd, aey divided by y is ae. So now I have this inside of this parentheses, and I have one y here. Well, if I only have one y here, what's being on this side of the problem? What is on this side of the problem that I don't want? Well, I don't want the parentheses. So if I divide both sides by bd minus ae, I end up with it over here. And oh wait, that's what y is. So if I solve this for y, Here we go. And if you want to go back and use a regular two linear equations and solve for them, you could do so. And this would say, oh, no matter what A is and B is and C is, that's where they're going. No matter what D is and E is and F is, that's where they're going to end up every single time if I have two linear equations like this. So we kind of come up with a formula for it as well. Now 62.2, let's go ahead and look at the next example here. And this is what they want us to notice on this, and what the reason why they threw this problem in here is that subscripted numbers confuse a lot of people. And in other words, and if you're taking any of the other upper level classes right now in high school, you may be taking some physics, right? And you would say acceleration 1 and acceleration 2, and they're two different accelerations, so we would subscript them with A1 and A2, but they're not the same, so I can't put them in for the same thing. And I have to do the same thing here. So these are subscripted A1x, B1x, C1x, A2x, B2x, and C2. These are not the same variable. A1 and A2 are not the same. But I'm going to solve it exactly the same way. So I just jumped down here and I multiplied the first one by B2 and the second one by negative B1. And for sake of time, if you need to pause it to see, work those out, that's what I did here. And that gave me these two equations. I simply add the two equations up, right? And that's going to get rid of that first term because it's, or the second term in this case, because the first term, these two got moved down. This is a B1, B2y. This is a B1, B2y. That's what canceled out, positive, negative. And because of what I was solving for was x on this one, not y. I get that into two equations. I factor the x out. I divide by what's left, and I have it in terms of x. I can't combine an A1 and an A2. They're not the same term. That's what all this whole thing for 62.2 is all about. Is let's solve for x, but we have A1 and A2, a B1 and a B2, and a C1 and a C2. Now, I have seen people do this, and if this makes sense to you and it helps you out, you can go through and say, instead of A1, I'm going to call that one D. Or sorry, A2, I'm going to call it D. Instead of B2, I'm going to call it E. And instead of C2, I'm going to call it F. And now I have this exact problem here, right? And that makes more sense in some people's heads. That's okay, whatever works for you. You could always substitute that in and then resubstitute it at the very end of the problem back into it, and you would get the same answer. Just because some people struggle with A1 and A2 not being the same thing. But we already know they're not. You can use either method.